brought an increased level of interest in mathematics and has, I guess, added to the variety of methods of teaching at mathematics teachers' disposal. So really, like, quite an exceptional individual, both at an academic level and on an entertainment level. Ladies and gentlemen, Professor, the Harvey Mudd Professor of Mathematics and mathematician, Professor Arthur Benjamin. Now, Professor Benjamin is going to make a mathematics presentation to start with, and then we'll have a Q&A, and at the end, a final kind of presentation again at the very end. So yeah.
Well, first of all, thank you for this award. It's really quite an honor, quite unexpected, and I really appreciate it. It's great to be here. Well, I guess just if I can show off for a few minutes, I am a mathematician, which means I combine my loves of maths and magic to do something I call mathemagics. But before I begin, by any chance, did anyone happen to bring with them this afternoon a calculator? If you have a calculator with you and you're pretty comfortable using it, raise your hand. I see one person. Anybody else? Two? And maybe one? Three. The three of you bring out your calculators. And you can stand up if you'd like.
There's a whiteboard marker.
That's, oh, great.
Just there on the...
So I need to first make sure that all your calculators are working properly. Would somebody get us started by giving us a two-digit number, please? How about a two-digit number?
54.
54. And another two-digit number. How about another one?
79.
79. Multiply those numbers together. Make sure you get 4,266, or the calculators aren't working. Are they all working? 4266? Yes? Good. Okay. Now, I noticed that took some of you a little time to get your answer. I'll give you a shortcut for multiplying faster on the calculator. There's something called the square of a number, which most of you know is taking a number and multiplying it by itself. For instance, 5 squared would be 25. 6 squared would be 36. 73 squared would be something bigger, right? So what I'm going to try and do is to square in my head 3 two-digit numbers faster than they can do on their calculators, even using the shortcut method. Now, the three of calculators, raise your hand so I see where you are. So I see 1, 2, 3. Okay, so I'll ask, there's 3 people here in the first row. How about 1, 2, 3? Each yell out a two-digit number, and if you would square the first, the second, and the third one, I will try and race you to the answer. So quickly, a two-digit number, please.
38.
38, great. Another one?
67.
67, one more?
27.
27. Would you call out your answers, please?
1444.
1,444.
4489.
4489. Oop, you did 37. I did 27. So do 27. One of us misheard. It might have been me. What do you? 729. Give them a round of applause. Let me try to take this one step further. I'll try to square some three-digit numbers this time. I won't even write these down. I'll just call them out as they're called out to me. Anyone at all call out a three-digit number. Anyone on our panel, verify the answer. If I get the answer right, give me a thumbs up or say, yep. If I make a mistake, let me know, and I'll try and fix it. A three-digit number, anyone?
212.
What was that?
212.
202 squared is 44,944. Yes? Okay, waiting for a confirmation. Okay, another three-digit number.
793.
793 is 628,849.
123.
Yes, 123 is 15,129. I've got that one memorized because people say that one a lot. One more three-digit number. Go ahead. 782. That's 611,524. Thank you very much. Try to take this one step further. Going to try to square a four-digit number this time. Now, I'm not going to beat you to the answer on this one, but I will try to get the answer right. To make this a little bit more random, let's go up the aisle. If I can get the first four of you to each call out a single digit between 0 and 9, that will be the four-digit number that I'll square. 3, 4, 6, 8. 3, 4, 6, 8. This will take a little time, so bear with me. 12 million, I think. $27,024?
Yeah.
Yes, good. Thank you very much. Now, I would attempt to square a 5-digit number, and I can, but unfortunately most calculators cannot. So they run out of room, what can you do? So since we've reached the limits of our calculators, I'd like to conclude the first part of my show by trying something a little trickier. Let's take the last number on the board here, 729. Would you each enter 729 on your calculator? And instead of squaring it this time, I want you to take that number and multiply it by any 4-digit number that you'd like. But don't tell me what you're multiplying by, just multiply it by any random 4-digit number. Don't make it too easy like 1,000 or 2,000, but just some random 4-digit number. So you should have as an answer either a 6 or 7-digit number as your answer. How many digits do you have in your answer? 6 or 7? 7. And yours? 7. 7. Is there any possible way that I could know what 7-digit numbers they have? Say no. Good. Then I shall attempt the impossible, or at least the improbable. What I'd like each of you to do is to call out for me any 6 of your 7 digits, any 6 of them, in any order you'd like. 1 digit at a time, I shall try and determine the digit you've left out. So starting with your 7-digit number, call out any 6 of them, please.
917568.
All right, remember the number you left out and don't forget it. You've got a 7-digit number, call it 6 of yours, please.
332934.
All right, I think I have yours. Finally, give me 6 of your 7. Really scramble them up this time.
489.
Let me do yours first. Did you leave out the number 1?
Yeah.
Yes. Did you leave out the number 3?
I did.
Yes. And yours is still giving me trouble. Do me a favor, if you would. Concentrate on the digit you left out. I can use all the help I can get. I'm getting a lot of nothing. Did you leave out a 0?
Yes.
That's why I was getting a lot of nothing. Let's give all 3 of these people a Thank you very much. For my next number, I have another question for the audience. By any chance, does anyone here happen to know the day of the week that they were born on? If you think you know your actual birthday, raise your hand. How about you, sir? What year, if I may?
1994.
1994. And what month?
February.
February what?
27.
27. Was that a Sunday?
Yeah.
Good. Somebody else. Yes, please. What year?
1990.
1990. And the month?
December.
December what?
7th.
7th. Was that a Friday? Good. How about way in the back? Go ahead, yell it out. What year?
1993.
93. And the month?
June.
June what?
23rd.
23rd. Was that a Wednesday?
Yeah.
Thank you very much. You know, this place has a lot of history, and there is something I haven't tried before, but there's an app for everything these days. And this calculator, when you type in the date, will go as far back as 1600 or as far into the future as 3000. So I'll ask you to give me a date, maybe not in the 1900s or 2000s, but any other century. And so what year would you like?
1824.
1824. Okay, so type in 1824. And what month would you like?
May.
May. Press the May button there and look at the May calendar. May what?
22nd.
22nd. Was that a Saturday?
Yes.
Oh, yeah. And it was cloudy too, I think. Yeah. Thank you very much. Anyway, are there any questions? No, seriously, so for the next 30 minutes or so?
Absolutely. Would you like to take a seat?
I would be honored to take a seat.
So I guess, everyone, if you'd like to think of a question or so, I'll just get the ball rolling. I have a couple. Obviously, Professor Benjamin, you've got some quite unique talents there. Do you feel that that's sort of nature or nurture, or that, like, where Where do you feel like your talent comes from?
I'm a big believer in the thousands of hours of practice theory. I mean, I think I've loved numbers for as long as I can remember, for as long as my mother can remember. I've been very, I've enjoyed playing with them. They were a game for me. And what you saw me do here mostly was a self-taught skill. A couple of things like figuring out the birthdays, I learned that from a book I read in high school. But multiplication and squaring and things like that, I mostly figured out on my own. But that said, I think without the thousands of hours of pleasant practice, that just idle time, really, I call it the product of a misspent youth, you know, is what turns that into doing it fast.
Sure, sure.
I think anybody in this room can learn how to do what I'm doing, can understand everything that I'm doing, but maybe doesn't have the hundreds or thousands of hours to invest to get as fast as what I'm doing. But that's okay. You can still get, you know, twice as fast, 10 times as fast as you can now, if you practice with the right techniques. So, I mean, nature certainly has a lot to do with human intelligence. I'm a big believer in that. But but I think in terms of acquiring a skill, I think it's largely a matter of practice.
Sure. Also, I mean, your research topics are, like in your papers, are an incredibly interesting, sort of diverse range of things. One of them I noticed was combinatorics and campus security.
Combinatorics and campus security.
Yeah, we have a few issues with campus security. I was just wondering, could you enlighten us?
Well, my area of mathematical specialization is something called combinatorics. That's the mathematics of counting. How many ways can you do this or that? And in this one paper that I wrote, it pertained to various locks that were on the buildings on our campus that consisted of 5 buttons, and you would press the buttons in certain combinations, and you weren't allowed to press a digit more than once in the combination. And the question is, how many combinations are possible? You know, is a 5-button lock very secure? So, it turns out the answer is like 1,081 different combinations that can go. And that's not very secure. You know, a persistent undergraduate could probably get in there within a couple hours if they really needed to know. You know, whereas with a 10-button lock would have millions of possibilities. And so that paper was devoted to counting not just the 5-button lock or the 10-button lock, but the n-button lock problem. How many solutions are there?
And just out of interest, how did you come to start performing Mathemagic? Did you just have a few friends who were really impressed with your abilities and kind of like snowballed from there?
Yeah, as a kid, I just loved showing off. Don't we all? And I enjoyed magic, performing traditional magic tricks I've enjoyed that for a long time. And when I was in high school, probably around year 9 or 10, I started performing magic for children's parties, birthday parties, little 5-year-olds, 6-year-olds, and doing the standard rabbit out of the hat, make the kids laugh, fall on your tush, that sort of thing. And that worked really very well. I did that throughout high school. And then when I started doing shows for older audiences, my father suggested that I put some of my number talent into it because he thought that was interesting. So I didn't think anyone would find it interesting, but I did, and to my surprise, they did too. They liked it, and so at least they liked it more than my card tricks. So I said, well, okay, if they like that, imagine if I could do bigger problems and faster, and I just took it from there. So and then it got all kinds of attention, and now I don't do the traditional magic so much, though I still love to study it and perform mainly what you're seeing here, mathematical.
Right. Well, at this point, does anyone in the audience have any particular questions they'd like to ask?
Yes, sir.
When most people multiply two numbers together, they take the individual digits and then multiply them all together and then add the numbers together. Is that the method you use, or do you just know?
Okay, so the question is, how did I figure out those missing digits, right? Right? How did I figure out when everyone had a 7-digit number, they called out 6 of their 7 digits, and I told them the missing one. That's actually the easiest thing I did up there. And I'm going to let some people here in the audience, maybe some of the math students here, show off for a minute and finish my sentence. Oh, that one, that was easy. Finish my sentence. It's all based on the magic property of the number 9. I heard a few of you say 9. 9 is right. What does 9 have to do with it? Allow me to write up here. So, now by the way, I'm going to share with you the secret of what I'm doing, but magicians generally don't reveal their secrets. And the reason we don't is because you never respond the way we want to. We've all made that mistake before. We never get the reaction we want. We want people to say, wow, that's clever, you're good. But you never do. How is it that you've responded most of the time someone's explained a magic trick to you? Oh, that's dumb. I thought you were good, but I just wasn't paying attention. So I will share with you the secret of the missing digit, but just remember how impressed you were before I gave you the explanation, all right? Is the deal? So, all right, so number 9, what does 9 have to do with it? Let me write down on this tablet as many multiples of 9 as I can. And somebody tell me, what do those numbers have in common? They add up to 9. If you add the digits, you get 9, right? 1 plus 8 is 9. 2 plus 7 is 9. 3 plus 6 is 9. Wait, there's an exception. Which one? 99. But that's okay, because 99 adds up to 18, which is a multiple of 9. So here's the deal. A number is a multiple of 9 if and only if the digits add up to 9 or 18 or 27 or 36. They have to add to a multiple of 9. So if we go back to the numbers here, originally, 1444, what do those numbers add up to? 13. So is that a multiple of 9? No. How about 4489? What does that add up to? 25. Is that a multiple of 9? No. How about 729? What do those add up to? 18. So is that a multiple of 9? Yes, and that's why I chose it. All right, so I have this multiple of 9 here. I'm going to take advantage of that. Now, someone with a calculator, take 729 and multiply it by your favorite 4-digit number. You'll get either a 6-digit or a 7-digit answer. So, someone go ahead, quickly give me, you have 7 digits again?
Yeah.
Give me 6 of your digits, please.
33, 29, 34.
332934. Now, I don't know what his 7-digit number is. I still don't know it. But I do know this. His 7-digit number has to be a multiple of 9, right? Because he started with a multiple of 9 and he multiplied it by something. So the answer still has to be a multiple of 9. So what am I doing as he's calling out his 6 numbers? Adding them up, exactly. So let's do that. 3 plus 3 is 6, plus 2 is 8, plus 9 is 17, plus 3 is 20, plus 4 makes 24. So what did he have to leave out in order to have a multiple of 9? 3 in order to get 27. Did you leave out a 3? Good, that's a good thing. All right, so question about what I'm doing?
I think that guy's missing number was 0.
Nah, okay. So, suppose he called out his 6 digits, and they add up to 27. Okay, 6 numbers, they add up to 27. Then what digit did he leave out? 0, or, the math majors say, maybe 9. You don't know. Do his numbers add up to 27, or do they add up to 36? You don't know. What do you do in that situation? You guess. But as a magician, you can do it in such a way that it does not look like guessing. And there are a couple of ways of doing it. One is the way that you saw me do. Right? I said, I'm having a little trouble here. Concentrate on that digit. I'm getting a lot of nothing. Did you leave out a 0? He said yes. I'm a genius, right? If he said no, I would say, oh, because it seems like you're thinking of nothing. Okay, concentrate harder. A little math humor there. Okay, I got it now. You left out the number 9, and you take your bow. All right? Now, if that's a little too sleazy for you, then a slightly more honest approach would be this. I'd say, pretend you just left out a 0 or a 9. I'd say, oh, this is very interesting. I see a couple possibilities. Tell me, did you leave out an odd number or an even number? And if he says that it's odd, then you know he left out the 9. If he says it's even, or a look of panic goes across his face because he doesn't know if 0 is even or odd or what, I'll just see that look of panic and I'll say, you left out 0, right? Yes. And you take your bow. Thank you very much. Other questions? What else? And you're my timekeeper, so I don't know.
Oh, yeah,
I don't have a watch here,
oh,
so
yeah.
you'll have to tell me what. Yes, sir. What's your question?
Do you have a favorite number?
What's a favorite number? Oh, there's so many favorite numbers that I have. As a kid, I think my favorite number was 9 because of all of its magical properties. As I grew up, as my tastes expanded, my favorite integer became 2,520. Any Math Society members here know what's nice, special about 2,520? You know what it is?
It's related to 52, I think.
No, not related to 52, although 52 is inside of it. That's not what made it special. In fact, it's a special number. It's the smallest number, the first number that has a nice property that would appeal to anybody who liked arithmetic.
Is it something to do with raising the digits to their own powers?
No, there are fun things like that. Numbers like 370 is 3 cubed plus 7 cubed plus 0 cubed, and that's very interesting. But that's not what makes 2,000.
It's the first number that's not interesting.
It's the first number that's not interesting, and that would make it interesting. Exactly. No, that's not what makes it interesting. I will tell you, it is the first number. By the way, is it a multiple of 9?
Yeah.
Because the digits add up to 9. Okay, that's a hint. Is it even? Is it a multiple of 5? Yes. In fact, it's the smallest number that's divisible by all the numbers from 1 through 10. That's what made it interesting for me. Okay, so as I grew up, some favorite number, that's 2,520. And then, but then you get your teenage years, you branch out, you get into things, you experiment with things like irrational numbers, right? Pi, E, the golden ratio, right? College years, you're into the complex numbers, fractals, psychedelic stuff like that. Anyway, my favorite set of numbers are the Fibonacci numbers, and that's actually what a lot of my research papers have to deal with. The Fibonacci numbers are as easy to understand as 1 plus 1, which is 2, and 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 13. What's the next Fibonacci number? After 8, then 13, we'd have 21. What's the next one? 34, and so on. They go on forever. And there are so many beautiful number properties, number patterns that exist inside of these numbers. Here, I'll just mention just a couple of them. Like if I like to square numbers. You square the number 3, you get 9. If you multiply 3's neighbors, you get 10, and they're just 1 apart. If I square the number 5, you get 25. If you multiply its neighbors, 3 times 8 is 24. They're 1 apart. 8 squared is 64. If you multiply its neighbors, 5 and 13, you get 65. They're 1 apart. It's kind of, beautiful stuff like that. Here's my favorite one, though. If I asked you for the largest number, we just talked about 2,520. If I said, what's the greatest common divisor of, let's say, 20 and 90. What's the largest number that goes into 20 and 90? If you think for a few seconds, you'd say it's 10. Okay? Get this. What's the greatest common divisor of the 20th Fibonacci number and the 90th Fibonacci number? Believe it or not, it's not 10, more poetic than that. It's the 10th Fibonacci number. Yeah, that's awesome. That's utterly beautiful, and it can be proved using elementary mathematics. I mean, using the type of math that I teach first-year college students at my school. So anyway, so that's just, I guess, a long diversion on a short question. Do we have time for...
Oh, yeah, absolutely, yeah.
Yes, sir.
Two questions in one. Do you like prime numbers, and what's the largest prime number you know?
Do I like prime numbers? Yes and no. As a mathematician, I like prime numbers because they're fascinating. They're beautiful. They have all kinds of mysterious and properties that we're still trying to understand. As someone who likes doing arithmetic, though, prime numbers get in the way. Now, in the very first problem that I did today, I asked for two-digit numbers. I think the numbers were 54 and 79, if I'm not mistaken. 79 is prime. Can't do anything with that. But 54, that's composite. I can break it up as 9 times 6. I can do 79 times 9, gets 711. Multiply that by 6 to get 4266. So composite numbers are much easier to use. So 79 times 53 would have been a much harder problem than 79 times 54. So I have a love-hate relationship with the prime numbers, is I guess what I'm trying to say. And what was your other question?
What's the largest?
Oh, the largest prime number that I know, and I only know this because it's easy to write down. It's 19 ones is the largest known rep unit prime number. So there's my favorite. The largest prime that I know, and certainly the one I can write the quickest. Yes, sir?
I don't know about the States, but also in this country, there's a lot of people who just really don't like maths at all. Like, can you relate to them, or like...
I can relate to them in the same way that I can relate if I walk into like an aerobics studio. And I mean, if somebody came up here to teach us all a dance step, even though this room might be filled with other math and science majors, I would be the last person in the room to learn the dance step, okay? My feet just don't learn that quickly. So I can appreciate that a lot of people, that certain things don't come quickly to everyone. On the other hand, I'm also a believer that if with diligence and practice, and maybe most importantly, with a good teacher, you can learn this material. And I think, you know, I know very few people in this world who hate all forms of music. You know, we may not all be into opera, we may not all be into jazz, but probably somewhere along the way we've been exposed to some kind of music that we liked, that felt good. And I think the same can be true of mathematics, that there's a lot more to mathematics than just doing sums. There's a lot more to mathematics than geometry, than algebra, than calculus. I think if we were exposed to it in a less computationally focused way, I think more people would see not just the applications of math, but the beauty and fun of the subject.
Why do you think it's like, it seems in maths that like a lot of students find most inaccessible of all the subjects they do, especially like in like high school? Like, do you think there's a reason for that?
Why is it so inaccessible? I guess two reasons. First of all, math is the only subject for which there, you know, always have a definite right or wrong answer. You know, you can write a paper on lots of subjects and your teacher can say, well, I give you partial credit on that, or that was, you know, okay, you make some good points, it could be improved, but in mathematics, you know, you get the wrong answer, you get the wrong numerical answer. You can't argue your way out of it, you know. I mean, you can learn from your mistakes, but so in some ways, people, I mean, I think if there were right and wrong answers to, you know, history questions or philosophy questions or economics questions, you know, as sharply as there are in mathematics, you'd have a lot of people saying, I hate those subjects as well, too. But I don't know. I think we teach people the wrong mathematics in high school. I think there's too much of an emphasis on calculus. That is, I think, yes, we all need to learn arithmetic and algebra, but beyond that, we should be able to explore. And yet, at least in the United States, the mathematics has been taught pretty much the same way for about the last 200 years. And it's as if everybody is learning mathematics so that they can fully understand the mathematics that governs the laws of nature. And if you're going to be a scientist and an engineer, you need to know that. But I think that's the wrong mathematics that we should be teaching people today. Today, if I had my way, we'd spend more time teaching people things like probability, statistics, discrete mathematics, game theory, fractals, number theory, and it doesn't have to be this big cumulative structure. You know, a few weeks of number theory, you'll love it or hate it. It's like jazz or opera. You'll love it or you'll hate it. Yeah.
Have you heard of Project Maths?
I heard of Project Maths, not by that name, no.
It's the new Irish curriculum, actually. It's the increase of stats and probability and less calculus, so just when you mentioned it.
I think that's a wonderful idea. I mean, let's put it this way. I think if there's one subject that, you know, if I had to choose between every high school graduate having been exposed to calculus or every high school graduate having been exposed to probability and statistics, I think probability and statistics would win hands down. I mean, calculus is useful for scientists and engineers, but you never use it in your daily life. Whereas statistics, probability, you are evaluating risks every day. You know, you take calculated risks every day, whether you're explicitly calculating them or not. It teaches you how to think in a different way. You know. Anyway, so I can get on my soapbox on that, but that's. But to do that, we need to offer them more courses, and I don't know the situation in this country like we have it in the United States. We need more qualified teachers who really have a passion for their subject. We don't make our high school teachers or elementary school teachers, primary school teachers, have a passion for the subjects that they teach, and that's very, very unfortunate. I think that's, yeah?
You know, I think I speak for all mathematicians in the room when I say that good maths jokes are like women in maths. They're very rare, but when you encounter them, they're truly splendid. So with that in mind, do you have any good maths jokes to share with us?
Oh, good math jokes. Good math jokes. Yikes. No, but I've got a good math song for you. Can I give you a song instead? Can you take that one? Maybe while I'm singing it, I'll think of a good math. I mean, the ones that come to mind are usually the very, very corny ones that I won't subject you to. But we mentioned the number pi earlier, right? Kind of the first few digits. Anyway, I gave you 100 digits, and that's a whole talk in itself. But a few years ago, in celebration of Pi Day, March 14th, I wrote a song that to celebrate my favorite number and one of its irrational properties. So there it goes. You might even recognize the tune. A long, long time ago, I can still remember how my math class used to make me snore. 'Cause every number we would meet would terminate or just repeat. But maybe there were numbers that did more. But then my teacher said, I dare ya to try to find the circle's area. Despite my every action, I couldn't find a fraction. I can't remember if I cried the more I tried or circumscribed. But something touched me deep inside the day I learned of pi. Oh, pi, pi, mathematical pi. Twice 11 over 7 is a mighty fine try. A good old fraction you may hope to supply, but the decimal expansion won't die. Decimal expansion won't die. Pi pi, mathematical pi, 3.14159265358. A fraction you may hope to define, but the decimal expansion won't die. Thank you. So I see we have time for me to do my one last little grand finale, and if you have any other questions, I will gladly hang out here afterwards, and please join me for lunch or do whatever you'd like, and I'd love to talk to you all. But anyway, the last thing I want to do is something I alluded to earlier. Those with calculators, bring it out. I'm going to try to square a 5-digit number. Now, not all calculators can do this, but a lot of the more recent ones can. So if yours can, that will be great. But to make my job more interesting for you, as well as for me, I'm going to do this last problem thinking out loud, so you can actually honestly hear what's going on in my mind while I do a calculation of this size. Let's create a 5-digit number. How about we go up this aisle? If I can get the first 5 of you to call out a single digit, that will be my 5-digit number.
7.
7. 6. 4. 3. 2. 76,432 squared. Great. Let me explain to you how I'm going to attempt this problem. I'm going to break the problem down into 3 parts. I'll do 76,000 squared plus 432 squared plus 76,000 times 432 times 2. Add all those numbers together and with any luck arrive at the answer. Now let me recap. Thank you. While I explain something else. As I do this last calculation, you will hear certain words as opposed to numbers creep into the calculation. Let me explain what that is. This is a phonetic code, a mnemonic device that I use that allows me to convert numbers into words. I store them as words and later on retrieve them as numbers. I know it sounds complicated. It's not. I just don't want you to think you're seeing something out of Rain Man here. There's definitely a method to my madness. One last instruction for my judges with calculators. Now, who's got an answer, just so I see a few of you? Good. Should have a 10-digit number beginning with a 5, ending with a 4. In between, I don't know yet. There's at least a 50% chance that I'll make a mistake somewhere in the middle. If I do, don't tell me what the mistake is. Just say you're close or something, and I'll try and figure it out, which can be pretty entertaining in itself. If, however, I am right, whatever you do, don't keep it to yourselves. Make sure everybody knows that I got the answer right, because this is my big finish, okay? So without any more stalling, except to say, 432 is composite, nice and composite. It's 48 times 9. I'll take advantage of that. Okay, so here we go. I'll start the problem in the middle with 76 times 432. 432 is 48 times 9. Let's use that. 76 times 48 is 76 times 8 times 6. That's 608 times 6 is 3648 times 9 is 3648 is 32,400 plus 432, 32,832. 32,832, double that to get 65,664. 65,664 becomes Jelly Judger. Jelly Judger is 65,664. Okay, haven't said any part of my answer yet, but I'm about to. Jelly Judger. Okay, next I do 76 squared. That's 5776, so I can say 5 billion. Take the 776, add that to Jelly. 776 plus the 65 is 841 million. Judger, Judger. Okay. Finally, we do Judger. 432 squared. That's 400 times 464 plus 32 squared is 185,600 plus 1,024 is 186,624. January, if I needed January, take the 186, add that to Judger. Oh boy, to get 850,624. Yes. Good. Thank you all very much. I'm my redemption.
Wow, I mean, clearly our latest honorary patient on the field is an incredibly gifted individual. But apart from that, we're immensely proud to have him as an honorary patron because of his not just his contribution in research to mathematics and academia, but also to his contribution to the teaching of mathematics and the increased interest. I think he's engaged us all very well here today. So for those reasons, I'd just like to thank Professor Benjamin again for accepting honorary patronage and for coming here this afternoon to address us all.
That my wife and daughter came here as well. This is my wife, Nina, and my daughter.